Assalamualaikum and hi everyone. We are from Group 2, going to present our SEL task for subject MTH3301, Real Analysis. Um, our lecturer's name is Dr. Idham and this group consists of 9 members. Next, I will pass it to Nick Hariz and Fatimah to explain to explain question from task 1.
So we are going to presenting task 1. I am Fatimah Ruqayyah binti Hassan with metric number 208071.
And my name is Nick Hariz Mustaqim bin Maharis, metric number 207622. So together we're going to present the solution for task 1. And to start, we'll go with the first definition for contractive sequence, which is definition 1. A sequence S equal to Sn upper limit infinity lower limit n equals to 1 is said to be contractive if there is a positive number 0 less than r and r is less than 1, such that modulus Sn plus 1 minus Sn is less than or equal to r modulus Sn minus Sn minus 1 for all n equal to 2, 3, and so on and so forth. With that, we are tasked to prove that S equal to 1 over n upper limit infinity lower limit n equal to 1 is contractive. With that, I'm going to pass the first step of the solution to Fatimah.
Thank you, Nick. So for the solution of this task, since modulus Sn plus 1 minus Sn is equal and lower than r multiplied with modulus Sn minus 1, where r is greater than 0 and less than 1 for all n equal to 2, 3, and so on. This means that modulus Sn plus 1 minus Sn over modulus Sn minus 1 is lower and equal to r. So from the definition, we have S equal to Sn with upper limit infinity and lower limit n equal to 1. And from the question, we have S is equal to 1 over n with upper limit infinity, lower limit n minus n equal to 1. So for the step 1, we let Sn equal to 1 over n. Modulus Sn plus 1 minus Sn over modulus Sn minus Sn minus 1 is equal to modulus 1 over n plus 1 minus 1 over n over modulus 1 over n minus 1 over n minus 1. This is equal to modulus n minus n plus 1 over n multiplied with n plus 1 over modulus n minus 1 minus n over n multiplied with n minus 1. This is equal to modulus negative 1 over n multiplied with n plus 1 over modulus negative 1 over n multiplied with n minus 1. Since it is modulus, this is equal to positive, which is modulus 1 over n multiplied with n plus 1 over 1 modulus 1 over n multiplied with n minus 1. Since this from here, we can cancel out 1 and we got modulus n multiplied with n minus 1 over modulus n multiplied with n plus 1. And then we can cancel out n and we got modulus n minus 1 over modulus n plus 1. This is lower than 1 for all n equal to 1, for all n equal to 2, 3, and so on. Then I will pass to Nick for the next step.
Thank you, Fatimah. Now we will move on to step 2. And for step 2, we suppose that some element of R where modulus n minus 1 over modulus n plus 1 is less than or equal to R, and R is less than 1 for all element of n equals to 2, 3, and so on and so forth. So we will start with modulus Sn plus 1 minus Sn, which is equal to modulus 1 over n plus 1 minus 1 over n. This in turn is equal to modulus n minus in bracket n plus 1 over and multiply in bracket n plus 1. This is equal modulus negative 1 over n in bracket n plus 1. Since there are 1 over n and this is modulus, and we have established that 1 over n is equal to Sn, it will be equal to modulus n minus 1 over n plus 1 multiply with modulus in bracket n minus 1 minus n over n multiply in bracket n minus 1. This is equal to in modulus n minus 1 over n plus 1, again multiply in modulus 1 over n minus 1 over n minus 1. In the first step, in the step above that we have established just now, R is equal or less than modulus n minus 1 over modulus n plus 1. We have the same exact one down here right now, which is modulus n minus 1 over n plus 1, which means that we can substitute it with R. So we get the entire equation equal to or less than R modulus Sn minus Sn minus 1. Thus, from the first definition, the sequence S equal to 1 over n upper limit infinity lower limit n equal 1 is contractive, since there is a positive number 0 less than R less than 1 such that it is less than or equal to R modulus Sn minus Sn minus 1 for all n equal to 2, 3, so on and so forth. And that is all for task 1 solution. We will move on to task 2. Thank you very much.
So now we will be presenting task 2, but first let us introduce ourselves. My name is Amirah Azahari. My metric number is 202446 and my partner is
Mardhiah Binti Illias, and my metric number is 205195.
So next. Okay, so the question is to prove theorem 1, which is if S equal to Sn and from 1 to infinity is a contractive sequence, then S is a Cauchy sequence by showing that limit from n to infinity modulus Sm minus Sn equal to 0, and hence S is Cauchy sequence. So for the solution, now suppose Sn is contractive. So modulus Sn plus 1 minus Sn less than R modulus Sn minus Sn minus 1, which is R is from 0 to 1 and n is the natural number. So to show sequence is indeed Cauchy, let m greater than n, which is we can write as modulus Sm minus Sn equal to modulus Sm minus 1 plus Sm minus 1 minus Sm minus 2 plus Sm minus 2 plus etc. Then minus Sn plus 1 plus Sn plus 1 minus Sn. So less than equal to a modulus Sm minus Sm minus 1 plus a modulus Sm1 minus Sm2 plus etc. And then lastly plus modulus Sn plus 1 minus Sn, which is we noted here as equation 1. So next. Now we can write the modulus Sm minus Sm1 less than equal R power of m minus 2 modulus S2 minus S1. Next, modulus Sm minus 1 minus Sm minus 2, which is less and equal to R power of m minus 3, which is modulus S2 minus S1, etc. And lastly, modulus Sn plus 1 minus Sn less and equal R power of n minus 1 modulus S2 minus S1. So next, I will pass the presentation to Mardhiah.
Okay, so from the equation 1, you can write the modulus of Sm minus Sn is less or equal to r to the power of m minus 2 times modulus of S2 minus S1 plus r to the power of m minus 3 times modulus of S2 minus S1 plus etc. until r to the power of n minus 1 times modulus of S2 minus S1. So if we simplify the equation, and it will equal to modulus of S2 minus S1 times r to the power of m minus 2 plus r to the power of m minus 3 plus etc. up until r to the power of n minus 1. So from this equation, we factorize the r to the power of n minus 1. So we will get modulus of S2 minus S1 times r to the power of n minus 1 times r to the power of m minus 1 minus n plus 1 plus r to the power of m minus 3 minus n plus 1 up until 1. And from here, we can write as modulus of S2 minus S1 times r to the power of n minus 1 times r to the power of m minus n minus 1 plus r to the power of m minus n minus 2 up until 1. And this is also equal to modulus of S2 minus S1 times r to the power n minus 1 times 1 minus r to the power of m minus n divided by 1 minus r. So we will get Sm minus modulus of Sm minus Sn is equal to r to the power of n minus 1 times 1 minus r to the power of m minus n over 1 minus r times S modulus of S2 minus S1. So this is less or equal to r to the power of n minus 1 divided by 1 minus r times S2 minus S1, modulus of S2 minus S1. So as n approaches to infinity, modulus of Sm minus Sn is approaching 0. So because limit n to the infinity, r to the power of n minus 1 is equal to 0, with a range of 0 is smaller than r and r is smaller than 1. So limit n approaching infinity, modulus of Sm minus Sn is equal to 0. Hence, S is a Cauchy sequence. So that's all from task 2.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Haswaniza Binti Abu Hanipar and my metric number is 206743.
Assalamualaikum and very good evening. My name is Nabil Helmy and my matrix number is 207613.
So we are doing the task 3. Let me read the question first. The question is lemma 1 is any Cauchy sequence is convergent. Prove the lemma 1. For the solution, let Sn be Cauchy sequence, then Sn is bounded by Bolzano-Weierstrass. Sn has a convergent subsequent Sn k to L. To prove Sn to L, for all epsilon greater than 0, there exists N1 is an element of positive integer such that Sn k minus L less than epsilon over 2 whenever nk greater than or equal n1. For all epsilon greater than 0, there exists n2 is an element of positive integer such that Sn minus Sm less than epsilon over 2 whenever n greater than or equal n2. So I pass the to the next presenter.
Thank you so much, Haswaniza. Now, we let n equal to max n1, n2, and choose nk such that nk greater than equal to capital N. For all epsilon greater than 0, modulus Sn minus Snk less than epsilon over 2. Hence, for all epsilon greater than 0, modulus Sn minus L equal to modulus Sn minus Snk plus Snk minus capital N equal to in bracket Sn minus Snk plus in bracket Snk minus L. And lower than equal to modulus Sn minus Snk plus modulus Snk minus capital L, lower than epsilon over 2 plus epsilon over 2 and equal to epsilon whenever n is greater than equal to capital N, where nk is greater than equal to capital N. Thus, S is convergent. This solution shows any Cauchy sequence is convergent. Hence, lemma 1 is proven. So I will pass this presentation to next presenter. Thank you so much.
My name is Alya Batrisyia binti Sabri, and my metric number is 208025. And with my partner, Iffa Fakhrina binti Yazid, and her metric number is 205597. And we will be presenting task 4. Next slide. Okay, so the question is, prove theorem 2, any contractive sequence is convergent. Therefore, first, we must show that the sequence is Cauchy, thus it is convergent. So for the first step, we will let S equal to Xn be a contractive sequence. All n is element of n. And then after that, Xn plus 2 minus Xn plus 1 less or equal than C times Xn plus 1 minus Xn less than or equal C power of 2 times Xn minus Xn minus 1 less than or equal up until less than or equal C to the power of n times x2 minus x1. So I will pass to Iffa to present the next step.
Okay, thank you, my partner Alya. Next, for the next step is then for m is greater than n. Xm minus xn is less than or equal to xm minus 2 up until xn plus 1 minus xn. It is less than or equal to c to the power of m minus 2 plus c to the power of m minus 3 up until c to the power of n minus 1 multiply with x2 minus x1 equals to c to the power of n minus 1, factor out c to the power of n minus 1, we will get c to the power of n minus 1 times with c to the power of m minus n minus 1 plus c to the power of m minus n minus 2 up until 1 multiply with x2 minus x1. It is equal to c to the power of n minus 1, 1 minus c to the power of m minus n over 1 minus c multiply with x2 minus x1 less than or equal to c to the power of n minus 1 times with 1 over 1 minus c multiply with x2 minus x1, and we will get 0 as n approaching infinity, since limit c to the power of n is equal to 0. Thus, xn is Cauchy and convergent. That is all from our group. Thank you.
From all the tests that were given, we learned that we are able to prove a contractive sequence and relate it with Cauchy sequence. And next, all of the group members are able to understand and relate the relation between contractive sequence and convergent sequence. So that's all from us. Thank you.